Alright, 8th grade, today we're talking about integer exponents. We're talking about everything that we can do with exponents. The first thing I need you to do is please put your name at the top of the note sheet that you're making, then put the date and the title, but I'm getting a lot of sheets with no notes, so please put your name. I'm getting a lot of sheets with no names, so please put your name. Integer exponents, so we're talking about taking any real number, and of course we know integer means all whole numbers and their opposites, so what's going to happen if we use an exponent that's either a positive or a negative whole number? First note we need is that exponents, or powers, or degrees, we know it goes by a couple different names, represent repeated multiplication. So if we're going to multiply 8 50 times in a row, then you don't need to write 8 times 8 times 8 times 8 50 times. You can just write 8 to the 50th power, or with an exponent of 50. Second note is any number raised to the 0 power equals 1, and that's kind of confusing a lot of the times. Why is that the case? A lot of people think, well, I know exponents mean multiplication, so if there's a 0 involved, it must equal 0. Not with the exponent of 0, though, and I'm going to try and show you why. If you had 2 to the third, we know that means 2 multiplied by itself 3 times, or 2 times 2 times 2. 2 to the second, then, would just be 2 times 2. 2 to the first, every number that doesn't have an exponent is really to the first. But 2 to the first is just 2. So why is 2 to the 0 equal to 1? Well, when you're multiplying these numbers over and over again, there can kind of be a 0 in there whether we write it or not. That's the identity property of multiplication. So whether we say it or not, there's kind of a 1 at the end. And it doesn't change anything. 2 to the first being 2, or 2 to the first being 2 times 1 doesn't really change it. So if we have 2 to the 0 tells us we're not multiplying any 2's together, but we can kind of imagine that that 1 is still there. That's how I think of it. The most important part is just that you remember any number raised to the 0 power equals 1. The next note, the number which is raised to a power is called a base. So if we have 5 to the 40th power, good thing we're writing it as an exponent or an exponential notation. Exponent notation. This would be the exponent we know, or the power, or the degree. But this other number, the number which is actually being repeatedly multiplied, this is called the base. That's an important vocabulary word or important term to know because of the next note. To turn a negative exponent positive, reciprocate the base. We can reciprocate the base. So reciprocate, we know from dividing fractions, means to flip or switch the numerator and denominator. And again, if there's no denominator, it's just 1. So let's think about what this looks like in practice. So if you have 3 to the negative second power. Well, to turn that exponent positive, we can just reciprocate. We can flip this and say that this would be the 3 is squared, but now it's on bottom, so we reciprocated it, and now the exponent is positive. So this would be 3 squared is 9, so this would be 1/9. Another example would be if we had 1 over, let's actually do 4 over 5 squared to the negative second, sorry. Well, to turn that 5 has a negative exponent. To turn that exponent positive, we'd have to reciprocate that part. We could take it to the other side of the fraction bar. So we'd have 4 times 5 to the positive 2. And that would just all be over 1 at this point. You wouldn't even have to write that. The last note is that if we had, let's say, 1/3, and I'm sorry this is kind of scrunched, to the negative third power, then to turn that exponent positive, we would reciprocate the whole fraction. Since that whole fraction is grouped and being raised to an exponent, this would be 3 over 1, or just 3 to the positive third power. You can reciprocate and then change the sign to be a positive. So there we go. Those are the first set of notes. Just 2 more that we have to talk about are a little bit more simple. Oh, I'm sorry for that, but I hope this is going to work even though my smart notebook is frozen. When multiplying with the same base, we can just add exponents. So if you have 5 squared times 5 to the third, we would have 5 times 5, 5 squared, times 5 times 5 times 5. 3 more because it's 5 to the third. Now, that's fine to write it all out, but we could also see that this first base, I don't know why this isn't working, this first base is just telling us that base and exponent tells us that we have two 5s multiplied together, and then we're going to multiply by 3 more, so we're just going to multiply a total of 5 5s together. This is 5 to the 5th. That's an easier way to write it. We can add the exponents only if the bases are the same. Next, when dividing with the same base, we can just subtract the exponents. And why is that? Well, what if we had 4 to the 6th divided by 4 to the 3rd? Well, we'd have 6 4s on top. And we'd have 3 4s on bottom. Oh no. And do me a favor, take your h, multiply it by 3. Now divide that number by 3. And you should get your same h, because if you multiply by a number and then divide by it, the effect kind of cancels out. So we can see why that's true as a fraction. If you're multiplying numerator and denominator by the same thing, you're not really changing it. But we can also just say that these cancel out. So multiplying by a 4 and then dividing by a 4 cancels out. Multiplying by a 4 and dividing by a 4 cancels out. Multiplying by a 4 and dividing by a 4 cancels out. What do we really have? We have 4 to the 3rd. And we could get that same answer just by saying we'll have 6 4s on top and 3 will cancel out because they're paired on the bottom. So we could just subtract and say 4 to the 6th. In fact, we could rewrite this as saying we're going to subtract, so we have 4 to the 6th minus however many are going to cancel out from the bottom. This would be 4 to the 3rd. All right, enough notes. Let's get to some practice. This first one is a doozy, but we notice we have the same base. 3 to the 5th times 3 to the 2nd times 3 to the 8th divided by 3 to the 8th times 3 to the 4th. There's a couple ways you could go about this. Some people might see that 3 to the 8th is repeated on top and bottom. They'll use that cancellation, just cancel those out right away. But let's just take it top first, and then we'll think about the bottom. So let's just worry about the top. 3 to the 5th times 3 to the 2nd times 3 to the 8th. Same base, we can add the exponents if we're multiplying them. So 5 plus 2 is 7, plus 8 is 15. So this would be 3 to the 15th. And on bottom, we have 3 to the 8th times 3 to the 4th. So we're multiplying with the same base. We can add those. 8 plus 4 would be 12. Then our second rule, or note we just took, said that if we're dividing with the same base, some are going to cancel out so we can subtract. So if we have 15 on top, and we're going to cancel 12, that get knocked off by the ones on the bottom, then we'll have 3 to the 3rd left. And 3 to the 3rd, we can do this mentally, means 3 times 3 times 3. 3 times 3, using the first 2, is 9. Then we multiply by that third 3. 9 times 3 is 27. Good. Second set to look at 2 to the 4th times 2 to the 0 power times 2 to the negative 9th times 2 to the 8th. Now some people, the first thing they're going to want to do is take that 2 to the negative 9th, turn that exponent positive by putting it below the fraction bar, by reciprocating it, and that works. Or we could just still add them all. We could say 4 plus 8 is 12, plus negative 9. 4 plus 0 plus 8 would be 2 to the 12th, times 2 to the negative 9. And we could still add these exponents. And we could say 12 plus negative 9, we'll have more positives than negatives, but different signs will cancel. We'll get 2 to the 3rd. 2 times 2 is 4, times another 2 is 8. Don't just multiply 2 times 3. That's not what that means. It's not 6. It's a common mistake. Finally, this last one says simplify. Because we have a variable here, we won't find a final answer, but we can simplify this so we have a single exponent. So we're just going to try and write h to a single exponent. We're going to try and cancel these out or combine them and put them together and figure out what it's going to be. So one option here, again, is just to add all the exponents on the same level where they're being multiplied together. And a lot of people will do that. They'll just add these exponents on top. And you can do that, that's fine. And then they'll add the ones on bottom and then subtract. But other people just like to deal with positive numbers, and that's okay too. So let's see what that would look like. To turn all the exponents positive, we have to reciprocate and then turn it positive. So h to the 19th power can stay up top, and h to the 22nd power can stay on bottom, but the other ones need to flip to turn positive. So that h to the 14th on bottom will only turn h to the positive 14 when we reciprocate it to the top, and h to the negative 4th and h to the negative 25th will only turn positive when we reciprocate them to the bottom. If that doesn't make sense, rewind and listen again, please. Now we can add how many h's do we have on top. We'll have 19 plus 14. That'd be 33, h to the 33rd power. On bottom we'll have 22 plus 4 is 26. 26 plus 25, it's like adding 2 quarters and another cent. That'd be h to the 51st power. And then again, we know that we can subtract at this point, or just think about cancellation. So if we subtract 33 minus 51, oh, that's a bad 3. Then we would get h to the, well, I'll play add ups here. H to the, it's going to be negative. We have more negatives. And 51 minus 33 is 18. 18. H to the negative 18th power. And if you want to turn that positive, you'd have to reciprocate it to the bottom of the fraction bar. Right now it's on top. So we just have 1 over h to the 18th. Whether you keep it negative and it just looks like a single exponent with no fraction bar, or whether you say 1 over h to the positive 18th. Either way, those are equivalent, and we talked about that. To turn negative exponents positive, you got to reciprocate them. As usual, I'm going to leave you with the practice problem, so here you go. 2 practice problems actually. The first one, 4 to the 6th times 4 to the negative 5th times 4 to the 7th times 4 to the negative 4th. I want you to simplify that all the way. Find out what number that's equal to. So don't use any exponents in your answer, just find it out all the way. And then for number 2, I want you to simplify to a single exponent, k to the 5th times k to the 3rd divided by k to the 12th times k to the negative 8. So you're going to have to figure out how to put those all together. Give me a single k to a single exponent. Whether it's positive or negative, numerator or denominator is up to you. Just do your best, and I will see you.